Hello students, today we are going to talk about complexity theory. So you remember that when we talked about decidability, we had discovered the set of decidable language, right? And this set of decidable language is part of a larger set of Turing recognizable languages, and we even saw that there are some languages that are not even Turing recognizable. So of course, among all the algorithms we're going to study to solve problems in concrete world, we are mostly interested in the decidable class of languages, right? For theoretical purposes, we can study the non-decidable ones, but now we are interested in this topic 10 in the more pragmatic aspect of this course, which is actually solving problems and actually running algorithms to solve problems, which we've seen are in our language, in our world, problems can be assimilated to languages, right? So, more or less, it's a question of encoding and all of that, but this is the equivalent of languages. So if we want to concretely solve problems, we're going to be interested in decidable problems, right? Decidable problems, obviously. And this is a very large class of problems, so we can have a lot of fun with it and solve a lot of problems, right? But we know we can't, for instance, solve the problem of are these two Turing machines equivalent, right? That this is outside. This is outside of the decidable set. So this is settled, right? We should not even try. Now, among the decidable problems, what is interesting is what are the problems, the languages, that can actually truly be solved in the real world. And technically all of them, right? Because for all of these languages, we saw that there is an algorithm, there is a Turing machine that halts, that says yes or no, and that is a decider for a solution. So technically, yes, all of them. Now, practically, and this is where complexity becomes interesting, practically, some algorithms are so complex, or in terms of the time and the resource they take, whether it's time or space, memory, that practically they are unsolvable. So they don't become as much interesting, right, if they are practically unsolvable. So we need to distinguish between among the decidable problems, what are the ones that are actually, practically solvable and practically unsolvable for, resources issue, right? This can be only resources issue now because we know that they are decidable. We know that there is an algorithm. It's only a question of how much time and space, memory, it will take. And so if you're skeptical of are there really problems that take that much? We have computing power now. These computers go ridiculously fast. Can we really face problems that are so complex that we cannot solve them in reasonable time? Yes, there are many of them, and it's important to classify them. So that's why we classify problems among the ones that are practically solvable and practically unsolvable. So as you've seen before in previous classes, complexity is conveniently distinguished between algorithms that have polynomial time for resolution and exponential time, right? So if we take a quick example, and you already know that. But if I take even like a high exponent here, the problem is to the order of n to the power of 8, and I compare that with to the power of n, in general, the exponential complexity, which is this one, is going to be much more time consuming than the polynomial complexity, right? If I take a number like n equals 120 in for this one, I'm still going to have like fairly reasonable number of iterations. I mean, this is still like very large, and it can take a long time for a computer to compute that, but it's still doable. This number 2 to the power of 120 is a number that is larger than the number of particles in the universe, for instance. So this number is like beyond reason in some sense. I mean, it's a very large number. So that's kind of the way we try to classify them. I mean, what is solvable in polynomial time, which calls this class of problem P, versus what is solvable in exponential time. And there's not just exponential. That's an example, and we know that exponential time is, it is strictly a larger class than polynomial, because of course everything that is solvable in polynomial time, you can solve it in exponential time, but the other way around is not true, right? It's not always true. Of course, you can find, again, example of problems you can solve in exponential time that you can also solve in polynomial time. Actually, it's easy to find an exponential algorithm. You can always try to find a harder algorithm, a worse algorithm for any problem. So polynomial time is a very good threshold. It's a very reasonable threshold, and there are many ways to look at it, and the book can give you more details. But basically, this is where you want to be. You want to be here, because here you enter into the realm of reasonable time, right? So there is really like a qualitative step that when we go beyond polynomial time, we enter into a category of problems that just won't be solvable by computers, practically speaking. They can be still decidable, right? They can be still in here, but practically speaking, the time they're going to take for increasingly large number of inputs is just it's just too much. I mean, it's just too much resources, and we're not equipped, at least with our current technology, but very likely for a long time, we're not equipped to solve these in a lifetime or in a reasonable time. So that's a very convenient threshold. Does it mean that I cannot find here n, where the exponential algorithm is going to be shorter than the polynomial time algorithm? That's not true. No, I can find an n if I take n equals 0, 1, 2, 3. I mean, until a certain point, and I don't know. I mean, how much we need to go, but even 10. I mean, until like a very large number of n. Actually, in this case, this is going to be faster than this, right? Because this increases much more quickly at the beginning. But then at some point, and this is what we're interested in, at some point, there is a point where this becomes obviously exponential. That's the idea. The curve goes like that, right? So and this becomes like just incredibly high and goes way beyond this. And when it starts going way beyond this is where we start having this unreasonable time behavior. So anyway, we want problems that are solvable by a polynomial time algorithm. So We call this class of problems P. And we want problems in P. Of course, we're not just interested in, it's easy to attribute complexity to an algorithm. That's something we know how to do, and it's very easy. For each Turing machine, you take a Turing machine M1, and you can attribute to M1 a certain, a certain complexity. That's something easy to do, and M2 is going to be, of N and etc. So there is no problem doing that. What is more complicated and interesting for us is to classify languages or problems, right? So P is a class, not a class of machines. It's a class of languages, of problems that can be solved by at least one Turing machine that has polynomial time complexity. That's what we're interested in, right? Problems, we don't need problems that can be solved only by, we need just one, right? It's really the same thing as a regular language, right? A regular language can be solved by a finite automata, or of course you can solve a regular language with a Turing machine, but and of course a lot of these languages can be solved by exponential algorithm, but we don't care about that because it's always better to have a polynomial algorithm. It's harder to find one also, usually. And so we always tend to try to go this direction in terms of search for algorithm and solution, right? There is a natural inclination to go toward polynomial algorithms, of course. So it's more complicated to decide if a language it's easy to decide if a machine is polynomial or not. It's more complicated to decide if a language can have one machine that solves it in polynomial time. So that's what P is. And so now what's interesting is that because we're naturally inclined to find polynomial time algorithms for certain problems, of course we want to figure out if all problems can be solved in polynomial times or not. And that is a tricky problem, right? Because that is a tricky question, because that means if I didn't find so far a polynomial time algorithm for this specific problem, does it mean that this is not in P? Well, not necessarily. Maybe I didn't find it, but that's not a proof that it is not in there, right? So same thing for decidable. To prove that a language is not decidable, we actually hooked all of these problems to one that we found and proved to not be decidable, and that was ATM. That was the one, and then everything is hooked to this one through reductio ad absurdum. Here, this is different. Here, it's very hard to find, and we're going to kind of do the same thing, but we do not have this kind of diagonalization method that allows us to find the one. Diagonalization is not going to work because it's not a question of yes or no here. It's a question of how much time, what is the order of complexity it takes. So finding an algorithm that is not solvable in polynomial, every question is a negation question. Finding the non-existence of a polynomial time algorithm for a language is very hard. It's always a very hard question because you cannot test all the algorithms. You can't. So we have a little bit of a problem here, is that we do not know any language that has been proved to not be polynomial. So it's complicated because we know we have all these languages and all these problems that are very hard to solve, and we have many, and we want to put them here. We want to write a cross here, but mathematically and rigorously, I am not allowed to put a little cross here. I cannot do that because I actually do not know if these problems are not polynomial because I've never proved it, right? It's easy to prove that some problems are here. That I can prove because I can just show them to you, and they are solvable by polynomial algorithms. You have a lot of examples in the book. Okay, so that leads us to the notion of NP and NP completeness, which are a very convenient way of trying to classify problems without having actually proved that there are problems outside of here. We can kind of use this notion to say, well, if there are problems outside of the here, these are going to be the problems that are outside. And we'll show you this trick. It's actually really, really interesting. So these problems are, they all have a Turing machine that can decide them in polynomial time, right? So they are decidable in polynomial time. Okay. Now, we create a new class on top of this one that is called NP, and it's instead of decidable, we actually say its NP is verifiable in polynomial time. And the nuance is that when you say decidable, that means that you actually decide what is in the language and what is not. And you actually decide the whole language. When you say verifiable, it means you are given an input, 1, and you can, in polynomial time for this input, decide if this input is in or not. So it's different to find all the solutions and to find, not just to find one solution, to be given an input and to verify if this input is in or not in polynomial time. You can look at examples in the book. So this one is, of course, much easier than this one, but it's a very convenient classification, because if something, of course, is decidable in polynomial time, then it is verifiable in polynomial time. So P is a subset or equal to NP, right? This we can be sure, and we can prove at least that if it is decidable, it is verifiable. What we don't know is that, is it true that if it is verifiable, it is decidable? So we know in this direction, right? We know that P has to be in NP or equal. Another way to describe NP that actually I find in some sense, the book emphasizes on verifiable, but I find in some sense it's better to call NP decidable in polynomial time by a non-deterministic Turing machine, right? So NP can also be described as decidable, so the same as here, in P time by a NTM. So what does this mean? That means that basically to be verifiable in polynomial time is the same thing as to be decidable, so stronger, but by a non-deterministic Turing machine. Here, as usual, we always assume, when you say decidable in polynomial time by a Turing machine, we always assume determinism, right? As we said before, a Turing machine is by default deterministic. Now, we are saying that if we relax these constraints, and as the book says, it's very important to understand that models of computation do not have the same robustness when you talk about decidability as when you talk about complexity. Complexity is very dependent on which model you take. So if you take a single tape or multi-tape Turing machine, you're not going to get the same complexity. You're always going to have better complexity with multi-tape. And if you take, so basically you're going to have, single tape, multi-tape, and non-deterministic Turing machine. And if you take a non-deterministic Turing machine, you have a much better complexity, because basically you assume that the complexity of a non-deterministic Turing machine to find a solution is not doesn't depend on the number of branches you have in the non-deterministic algorithm. It depends on how far you go in one of the branches, the accepting branch. So you can have 10 branches in parallel, right? You can have many branches in parallel. But if in the end you took, 2 steps, you test all of these branches, but you took 2 steps on the last one to find the solution, the complexity is 2, right? So that's really small, right? It's, so you assume that basically all the branches are going simultaneously, which is not possible really with a computer as it is now, because you really have to, I mean, you can do parallel computing, right? But still it's going to take more resources, right? You're going to expend spend the resources. So if you multiply that too much by branches of branches of branches, at some point you hit the wall. What is interesting is that something like quantum computing might challenge that at some point, because if you can have really 2 distinguished sets that can coexist in the same time, then yes, you can branch seamlessly without having to visit all the branches. So anyway, that's just a side note. So just to note, so the complexity is going to depend on which model you take, right? And so a non-deterministic Turing machine is much less complex. So there are variations. Now, these ones, multi-tape or single tape, doesn't change much. If you do single tape or multi-tape, you have a difference of complexity, but it stays. If it was polynomial before, it is polynomial after. If it was exponential before, it is exponential after. The difference between both is a polynomial difference. It's a polynomial step. The difference between this and this is an exponential step. You can, with a non-deterministic Turing machine, you can take something that was exponential complexity and make it polynomial complexity, because it's you radically increase the power of your machine. Like imagine it's like running an infinity of Turing machines in the same time. Of deterministic Turing machine at the same time, so it's incredibly powerful. So yes, it changes everything to be here or here. And that's why when we say decidable in polynomial type by a non-deterministic Turing machine, we are actually not saying much in some sense. I mean, we are saying much, but it's a much larger set of problems in some sense. Yes and no. Actually, that's what we don't know. This is the definition of NP. Okay, so I should just make this clear. These are 2 possible definitions of NP. And the problem is that we don't know if P is strictly a subset of NP, or if P equals NP. And so we don't know which one of these is true, right? So that's why if we say subset or equal to NP, that's fine, because this is true in both this case and this case, right? If you're in P, you're in NP. If you're in NP, you might be in P. We don't know actually if it's always true, right? So, but we suspect that this is the case, because we find so many problems that are in NP that are verifiable in polynomial time. So they are still interesting, right? They are not these problems that are just way beyond reason, right? They are very, what we call hard problem, right? So if you want to make it oversimplistic, you can say easy and hard, right? I mean, it's not the best like rigorous definition, but that kind of works. But hard, but might be doable, because at least we have the possibility to verify a solution in polynomial time, and we know that it is decidable in polynomial time by a non-deterministic Turing machine, right? So So we're interested in these two classes of problem, and what we want to know is how we can relate them to each other. And we know that there are a set of problems that are likely if, again, I cannot make a cross here because that would be acknowledging that this is the right model, what they could be equal, right? But if there is a cross here, we know a bunch of problems that should be in there because we've worked really hard for decades on these problems and we've never found a polynomial algorithm for this problem, right? They have always been in NP. We know we can solve them. I mean, we can find that a solution is or is not a solution, that an input is or is not a solution to this problem in polynomial time. We know they are there in NP, but we have no clue. We didn't find a polynomial algorithm. So we suspect that there are problems here. Now, the problem is that how can we make this classification rigorously if we don't know that there is a space between the two and we cannot call this something, right? So that's how we came up with the notion of NP completeness. So NP completeness, so if this is, so I'm gonna put that inside. If this is NP, so you remember how, how for non-decidable and undecidable, Turing recognizable, but these are undecidable, obviously. You know how we found like ATM? And then we were able to find a whole network of other undecidable problems through reduction. Well, we want to do the same thing with NP. Again, we cannot find a problem that we can prove to not be in P, just the way we did with ATM. ATM, we proved it was not decidable. So I'm going to write P like that with dotted line, because again, it might not be an inner circle of NP. It might be equal to P, right? So this dotted line means we don't know. It might be an inner circle, but it might be the whole bigger circle, right? What we want to find is are problems that can be considered to be at the border of complexity of NP, right? We know that NP could be potentially a larger. We know that NP is equal or larger, right? Because to say that something is solvable by a non-deterministic Turing machine is not as much as saying that it's solvable by the deterministic Turing machine, right? So again, this is deterministic Turing machine, which we call usually just Turing machine, right? We don't specify. And this is solvable by a non-deterministic Turing machine. Okay, so this is more potentially harder. What we're going to do is use the notion of polynomial mapping reducibility. And polynomial mapping reducibility is really the same notion as reducibility, mapping reducibility we've seen in decidable problems or undecidable problems, is that what is the formalism that is used in the book for polynomial mapping reducibility? Yes, it's A is polynomial time mapping reducible to language B. It's like this, right? If there is a polynomial type computable function f such that W is in A is equivalent as f of W is in B. So in other words, if you can solve B polynomially, you can solve A polynomially, right? So if B is in here, you know A is in here as well, because polynomial times polynomial, right? So basically, you could say that in this case you have, I mean, this is going to be it's not like rigorous, but schematically, you have B cross with F is A. So if B is polynomial and F is polynomial, then A is necessarily polynomial. Why? Because polynomial times polynomial is polynomial, right? If you take, n to the power of 4 times n to the power of 2, you still get, n to the power of 6. So you will still get something polynomial. You need the jump for exponential time, and you need to have some kind of exponential parameter. By the way, when we say exponential, it's I forgot to mention that at the beginning, but it's really assimilated to the typical brute force search. And it's why it's easy to find polynomial algorithms usually, because it's really looking for all the solutions, right? So just something like looking for all the paths, for instance, in a program where you have conditionals, you have, let's say, 20 conditionals in your program, right? 20 if, else, then statements, looking for all the paths. At the worst case, it's going to be 2 to the power of 20, right? So that's typical exponential. So if you want to make this polynomial, the search for a path, you're going to need to find a smarter way of doing it, like just use a symbolic executor to see which paths are feasible or not, or things like that. But at the worst case, you're going to get an exponential search if you just search for everything. So usually the brute force search is kind of the typical exponential case when looking for all the solutions in a graph or things like that. Okay. So if you multiply polynomial by polynomial, if you apply polynomial to polynomial, you stay in polynomial. That's a very interesting idea. So now the question is, can I find a problem in NP that is in some sense so hard and so complex that if I solve it, I solve everything in NP. I mean, I solve everything polynomially in NP. So the idea of ATM, although I cannot find something that is non-polynomial, I can find something that is in NP, solvable by a non-deterministic Turing machine, that is such a powerful problem that I can use it just the way that we use reducibility here with the function. So it's going to be basically my F, right? I want to find, actually it's more or less, actually it's not going to be my F, it's more like going to be my my B. It's a special B, we could call, a B star. That is such that once you solved it, you have actually a power. You have to understand, like, solving a problem, considering having it as an assumption that I can solve this problem, right? I don't care if it's polynomial time or non-polynomial time. I can solve this problem. I can use that as a pony. I don't know how to say that. As a ladder, I can piggyback on this problem to solve other problems. That's what this does, right? I piggyback on B to solve A using an extra little transformation function, right? Or additional polynomial function. Here, we're trying to find a problem. The way we're trying to solve the problem of finding the extreme problems, the ones that if there is an outer circle, the one that are in the outer circle, the way we're going to do it is by saying, let us find a problem that is so hard that once we solved it, we have the power to solve everything else here in polynomial time. And that's the definition of NP-complete, right? So NP-complete so you can say, B star is NP-complete if and only if for all other problem A in NP, right? Not just P, in NP, I can reduce, let's use the formal. A is polynomially reducible to B. That means I can actually solve A in polynomial time from the answer solving B, right? I just need like a polynomial extra step, which is basically, in our context, nothing. It's basically nothing, right? It's computationally nothing. Not nothing, it's doable, right? It's computationally doable. So if we solve this problem, basically, we solve everything polynomially. We can find a solution for all of them. But what is interesting is that it's not the idea, oh, we need to try to solve it. It's more like, no, this problem is likely to be the representation of a class of harder problem because its power is such that it can solve all the problems polynomially using its solution. And this problem is SAT. So it's a SAT problem. So it's not B star. B star is just an example of this, starting from this B. It's called SAT. It's a problem of satisfiability. The problem of satisfiability, you can look at the details in the book, but basically it's a problem of, I have a logical formula, right? So say, you know, a proposition P equals x1 or x2 and not x3, is there a combination of these such that, what is the combination of these such that P is true, right? Given that all of these are Booleans, right? So, well, to make P true, I can make one of these true, and this has to be false, right? So if I make one of these true and this false, I have P true, for instance. That's the problem of satisfiability. So I'm not going to go into the details of why this is NP-complete. But you can look at it. I mean, look at the proof in the book. It's actually really, really interesting. The basic idea is that you can find so a translation function, the equivalent of f here, that we call phi in the book, that is going to take a table of Turing machine configurations. So you have configurations here. And one of them, if you have and each configuration follows the preceding one by following the transition function. So these are succession of configurations, valid succession of configurations of the Turing machine for a specific problem A, right? We want to show that for all problem A in NP, I can solve it in polynomial time once I solved SAT. And the way we do it is using this table, we can show that if you have an accepting configuration in the table, and each step here is, you can describe all the conditions for that, oh, I have an accepting configuration and they are all licit succession. So we use like a 2 by 3 square to show that, okay, this, according to the transition functions, this piece can be before this piece. And you do that for all little pieces of this table. So basically you can see as a digitalization of a Turing machine. So a Turing machine, you know, as you remember, you know, it has a set of states, an alphabet, a tape, transition function, Q accept, Q reject. Okay, And so that's the definition. If you try to digitalize that into basically zeros and one, into true and false, so it's a kind of a, it's like taking a picture and transforming it into zeros and one, right? It's really digitalizing a Turing machine to transform it into 0 and 1, true and false. Then you can see how you can make it look like, oh, it is about solving the problem. Is what is the right combination of these booleans, so that the formulation at the end is true, solution or not solution, right? And so finding the right combination of all these, so that's a huge formula. You have to imagine it's going to be a huge, even for a small Turing machine, it's going to be a huge formula. But that's not the problem, because SAT doesn't say, oh, it has to be a small formula. It just says you have to find a combination of these x1, x2, x3. That's why it's actually exponential, right? I mean, it's why it's exponential. It is a hard problem. It's a huge formula. But once you have the formula and the transformation to the Turing machine into, into phi, the formula, this transformation, it is polynomial. To transform it, and you can see encoding is always polynomial. It's not going to be a problem. Encoding is not going to, you're not going to have to search through a space to encode. You just have to, it can be a tedious thing, it can take some time to encode, but it's going to be a reasonable time. So this is polynomial. Once you have the encoding into the formula, then the formula, you put it into SAT, and SAT is going to say yes or no, right? It's going to solve your problem. I mean, it's not going to say yes or no. It's going to actually, SAT is solving the problem of what is the right combination. And basically, it's going to solve the problem of what is the solution, what is accepted and rejected by your Turing machine. So you see that once we can do that, if we assume we can do that, we only have one polynomial step to solve any problem by any Turing machine in NP, right? Deterministic or non-deterministic Turing machine. So that's why SAT is so special, because the very way the problem is formulated, it is kind of a universal Turing machine in some sense. I don't want to say that because it's more of a universal, like non-deterministic Turing machine, but it's another version. It's a specific problem that can be into which any other problem can be translated into through polynomial transformation. So SAT is NP-complete by what we just said, right? I mean, I didn't prove it. I just gave you the gist of the proof. You can look at it in details in the book. It's really interesting. I invite you to do that. So now I can relate other problems to SAT. I can say, well, what are the problems I know to be reducible, polynomial reducible to SAT? Well, you can say, what are the problems I know if I solve this problem, I have solved also the SAT problem. So the other way around, right? Now we have an anchor, and we can relate other problem to it, right? Because I know that all the other problems can be solved from SAT, right? But so, I can solve any problem in P or NP from SAT. That's what we just proved. Now, what is interesting is that I can show that the other way around. If I solve the click problem, I have solved the SAT problem, right? And if I solve the Hamiltonian problem, I have solved the SAT problem. So I can find now my network of harder problems. And these harder problems are likely, if there is a difference between P and NP, they are likely to be on this outer circle, right? So we're kind of using the same like reduction principle as we were here on complexity issues. And so you have all these networks. So in some sense, I mean, my diagram here is very approximative, but in some sense, SAT allows us to find problems at the corner of a network of problems at the corner of NP. I mean, if there is such a thing as a corner of NP, if P is not equal to NP, we know that these problems are necessarily going to be not be in P. They are not going to be in P. They are hard problems. Basically, they are hard problems. They are intrinsically hard problems because they allow you to solve any other problems polynomially. So another way to put it is that if SAT is in P, then P equals NP. So another way to put it is to say if SAT is in P, then everything is in P. So, okay, so we're using this mechanism to say we don't know if P equals NP, but we know that these problems, if there are some problems who are in NP, and I repeat myself because it's just the only way to say if some problems have to be in NP and not in P, these are the problems. Because if these problems are in P, everything is in P. So basically we say that if these problems are easy, everything is easy. Another way to say if this is easy, everything is easy. If you say in everyday language, if doing this thing is easy, then doing everything is easy. Well, you're obviously talking about something that's hard to do, right? When you say, well, if that is easy, then everything is easy. Well, that's exactly the case here. We're saying we cannot say it is hard. We cannot mathematically prove that they are harder. Why? Because, to be honest, we still don't know if there is a polynomial algorithm to solve a SAT, right? There might be. We don't think there is. But it's very hard to prove that there is none because we cannot try all algorithms. And that's actually an undecidable problem. Trying all algorithms to discover all possible algorithms for a problem is here. It's undecidable. We cannot prove that. So what can we say? Well, we can say something else. We can say, well, if this is an easy problem, then everything else is easy. It's another way to say it's hard, right? We can't say it's hard because we don't have the proof, but it is. But it is in this different class of NP-complete problem. And not everything here is NP-complete, right? You can find a lot of easy problems to solve, like regular language. Is it a regular language? That's in P, right? Regular language, it's in P. Well, if you solve the regular language problem, you have not solved all the problems polynomially. You cannot piggyback on regular language to solve SAT or click. And these are examples in the book if you don't see what I'm referring to. So anyway, I've been circling around a lot, and I apologize for that. I just want to make things clear. Yes, I invite you to look at examples in the book of the Hamiltonian path problem, the subset sum problem, other little problems like that can make this a little bit more concrete. But basically, I wanted you to have this notion of P, NP, and what is really NP. It's not technically NP-complete. It's not technically the outside of P because we don't know if it's the outside or not, right? But it's a class of harder problems in general, right? These can be reasonably called harder problems. I wanted you also to understand that when we say NP, okay, this doesn't mean non-polynomial. Again, we don't know, right? So it's not like non-polynomial. It means can be solved by a non-deterministic Turing machine in polynomial time. Or another description is verifiable in polynomial time. So these are important notions. And when we say exponential, well, we know that NP is a subset of exponential. So exponential is a larger class, and some of these some of these problems can be considered as exponential. It's actually kind of hard to know if they are really on the side of P or on the side of exponential. Because again, you can always find an exponential solution for a problem, but as we said, that's not the end of the story. We always try to go down to easier, better algorithm, and that's not enough. You just need to find one polynomial solution to a problem to declare it in P. And as long as you didn't find a polynomial solution, that doesn't mean it is not polynomial. So except for the specific problems where you have proved rigorously that it is in there, and there are some, and we can actually pinpoint at some problems that are specifically in there. Okay, so I hope that makes sense, and that you find this as exacting as I do, and this is as you can see, more practical, because here we're getting really close to the question: can we actually, solve this problem or not in a reasonable time? Time is limited. We have limited lifetime, whether we want it or not, and we have to take that very strong constraint of human condition into into account, and that's what we're doing here. And this is very, very fascinating topic. Next topic will be also on completeness, but on the space side of things, memory side of things. Thank you.